Okay, so let's review Unit 5, 2D, force and motion. So, like in the last unit, we dealt with forces, but all the forces lined up with the x and y axis. So, you're going to have two types of problems here. You're going to have a hanging sign problem. Okay, so you're going to have here's like some fixed thing, and there's going to be a sign right here, kind of like what we did. Now they might be equal angles, they might be unequal angles, I don't know. And maybe we're trying to solve for the mass, maybe one of the tensions in the string. But the point is that when you draw the free body diagram of this, you have mg, you've got a tension force like this, and you got a tension force like this. And so that's one kind of problem. Then you're going to have an inclined plane problem where, here's my object, and there might be an applied force, there might not be, it might just be sliding down. You have to really look at the problem to draw the free body diagram correctly for both of these. Okay? But if I draw a free body diagram for this guy, there's going to be a force like this, there's going to be mg going down, there's going to be a normal force going up, there might be a force of friction like this. Now if it's sliding down the incline, the force of friction will be pointed up the incline. So you got to be careful, not just go based on what I'm doing here. You got to keep it general. But in both of these cases, here and here, some of the forces are not lined up with the xy axis. So make sure you use the procedure. Use given, find, and solve. Okay? Then draw the free body diagram. Then identify your x and y direction. In this case, I'll make x like this and y like this. Then you take the forces and you break them up into their x and y components. X component, y component. X component, y component. Now you use the geometry of the right triangles that you get there. Like in the take-home test, remember they gave us this angle, but that allows you to get this angle. So use these angles to get the x and y components expressed correctly. In this one, you want to take your x and y axis and make x up the incline and y perpendicular to the incline, because that way most of the forces now, 1, 2, 3 out of the 4 forces, are lined up with the x and y axis. So there's only one force you have to break up into its x and y components, and that's the force of gravity. So here's gravity, here's its y component, this is the component of the weight that's pressed into the incline, and here's the x component, that's the part of the weight that's trying to pull it down the incline. That's why things coast downhill, is because of this force right here. Now this is your angle of incline. If this is inclined up theta, then this gets rotated by the same theta. So your angle is measured from the vertical rather than the horizontal. So the sine and the cosine kind of get mixed up here. This is the adjacent leg. This component is the adjacent leg. So this will be your weight times the cosine of the angle. This is your weight times the sine of your angle. So we've just finished step 3 for both of these, and that is identify your x and y axis and break up any forces into their x and y components that you need to do. Okay? Then you just sum the forces in the x direction equals ma in the x direction. Sum of the forces in the y direction equals ma in the y direction. Now in this problem there is no acceleration, right? So they'll all be equal to 0. But in this problem there may or may not be acceleration. I think on the test I actually give you acceleration. So I don't know. No, actually b is constant. But in any case, I could give you a problem where there is acceleration, and so you have to be careful. But what is the direction of the acceleration? It will be constrained to an acceleration along either down or up the incline. So there won't be any acceleration in the y direction, only in the x direction, if there is any at all. Okay? And then those equations allow you to go to step 5, which is just to solve for your unknown. And make sure, if there is friction, make sure you know, okay, force of friction equals mu times the normal force, and, you know, force of gravity equals mg, that sort of thing. Okay? So that was force. That was section 7.1, all about force. Okay? The next problem was motion, projectile motion, where the velocity now has x and y components. So the velocity is now in 2 dimensions. Okay? Because before, all we did in unit 1 and 2, all our motion was constrained to move along a straight line. But now we're going to have motion that, projectile motion, where the velocities can have x and y components to them. Now the first kind of problem, the simplest one, is a cliff problem or a bomber problem. Cliff problems and bomber problems are the same problem. You have an object that has an initial velocity that's all horizontal. And then it goes splat, okay? And here's the final velocity just before it hits the ground. And by the way, if I ask you for the final velocity of the projectile, it's not 0. Okay, if that's the velocity just before it hits the ground, okay, it's kind of stupid to ask, well, it's 0 because it hit the ground. Duh, no, that's not what I'm asking for. So anyway, if you look at a free body diagram of a projectile, the only force acting is mg. So therefore, the only acceleration is the acceleration of gravity in the y direction. So that gives you the 4 kinematic equations in the y direction only. Okay, you know, Vy equals V naught y plus A times t. But what is A? Negative 9.8 meters per second squared. Of course, then you have delta y equals Vy plus V naught y over 2 times time. Delta y equals V naught y times t plus 1/2 a t squared, and a is the negative 9.8. Vy squared equals V naught y squared plus 2a delta y. Remember that delta y here is negative, right? It's falling down. And then there's only one kinematic equation in the x direction. Since the acceleration is 0 in the x direction, the only acceleration is in the y. There's no acceleration in the x direction. That means that delta x equals V naught x times t. If you put the plus 1/2 at squared on there, it goes away. It's 0. So this is all you got. Make sense? Okay. So now the link between these two is time. Now here's one of the hints. Usually you can find the time by knowing how far it falls down. Doesn't matter how fast it's going. Doesn't matter what the initial velocity in the x direction is here. The time it takes for it to fall down is the same. I mean, if you shoot a gun and you point the gun horizontally, how long does it take for the bullet to hit the ground? Well, it's the same as if you just took the bullet and dropped it. It's the same amount of time. It's just that the bullet is going so fast in the horizontal direction, in that small amount of time it takes for it to fall, it goes a long, long way. Okay? Now, if you tilt the bullet up, yeah, then you got different things going on. And remember, we're neglecting air resistance here, of course. The other kind of problem you're going to get for projectile motion problem is the classic football kickoff problem. Well, I think in the take-home test it was an arrow, but you shoot an object with some initial velocity, and it goes like this. Okay. Now, quite often they want to know how far does it go. That's the range. How high does it go? That's delta y max. Okay. Now there's a few tricks to being able to solve this problem. if they want to know the total amount of time in flight, the time it takes for it to go from here all the way over to here, what's the trick? What's delta y? If you start on the ground and you end on the ground, you add a total delta y for the whole thing of 0. So you can use the third kinematic equation, delta y is 0. You can divide both sides by time. That gets rid of the first time. This is a quadratic equation, isn't it? Look at this. If I rewrote this so that it equals 0, this would be a quadratic equation in time. And quadratic formulas usually have two answers. The first answer would be 0, 0 time. At 0 time, it has a delta y of 0. Yeah, but that's pretty boring. And I want the time it takes for it to go from here to here. So set delta y equal to 0. Divide both sides by t. You're going to have a t left over right here and solve for it. And that'll give you the time of flight. Now, if you want to find delta y, its maximum height, well, you know that the velocity in the x is still there, right? But what's the velocity in the y right here? It's 0. The velocity in the y at the top of its flight, it's the y component of the velocity at the top of the flight is 0. So that allows you to use the fourth kinematic equation to solve for delta y. What is the maximum height? Just solve for delta y from this equation. You know what v naught y is, right? Because look, here's v naught. Now I have to give you the launch angle, theta. So this is v naught cosine theta, and this is v naught sine theta, where theta here is the launching angle. And that will allow you to solve the projectile motion problem. And the last thing we covered in section 7.3 was uniform circular motion. Okay, uniform circular motion. An object moving in a circle. Now, I'm going to give you two possible kinds of problems on here. One of them is an object on a string. Now, I'm going to keep it simple. I won't include gravity on this part, okay? Because if I did, it's a little bit more complex. It's not bad, but I don't think you guys are ready for that yet. Here's a massive object, and it's moving around like this. And I've got, if I drew a free body diagram, there'd be a string pulling on it. That would be your tension force. So it's your tension force that's making this thing go in a circle. Now we said that the acceleration that makes things go in circles is the centripetal acceleration. It doesn't change your speed. It changes the direction of your velocity vector at a constant rate. And that makes you go in a circle. And we proved that the centripetal acceleration equals v squared over r. I don't require that you know that proof, okay? But I do require that you know this. And by the way, this makes intuitive sense. Try, walking or driving in circles, and you'll say, hey, the faster I go, the more acceleration I feel. And that acceleration and that centripetal force, when I multiply by the acceleration by the mass, is always directed towards the center. Even though you feel as if you're getting pushed the opposite way, you're actually getting pushed towards the center of the circle. You drive around in a car, you slide against the door of the car, you don't have your seatbelts on or whatever, it's pushing you towards the center of the circle. So the centripetal force is equal to mv squared over r. And now, so this, if the only force acting on your object is the tension force of the string, then you can say, oh, that tension force is my net force, which is the centripetal force equals mv squared over r, and you can solve. The other possibility is that it's a car going in a circle. Or it could be a person walking in a circle. So here's the car going in a circle, but gravity is trying to pull that car down. So what's supporting the weight of the car? The normal force. What force is applied to the car that's making it go in a circle? It's the force of friction between the wheels and the car. If you didn't have any friction between the wheels and the car, you can't turn. That's what happens when you drive on ice. You start slipping. Okay, you can't turn because you can't change your velocity if you don't have any friction between the wheels and the road. All right, so now you can say, well, the force of friction is equal to the centripetal force. This is the force as you go around the circle. It's the friction force that's making you go in a circle. So it's equal to mv squared over r. And now you can solve problems. But we also know if what I'll ask you is, what's the maximum possible velocity you can go with before you start slipping? So that means you use the maximum possible static friction between the wheels and the road. Remember, it's static friction because the surface of the wheel and the surface of the road are not slipping with respect to each other. So even though the car is moving, it's still static friction between the wheels and the road that you've got. So this will equal mu, the static friction coefficient, times the normal force. And in this case, the normal force is just equal to your weight, and you can solve any problem from there. So when you look at this chapter, or this unit, it's all about doing the stuff that we did before, but now we're applying it in 2 dimensions. Here we've got forces that need to be broken up into their x and y components. Here we have velocities that have x and y components. Okay? Here we have forces that are changing direction as we go around a circle. Okay? So it's basically kind of like what we did before, but we're extending it to more realistic situations, right? I mean, when you move around in 2 and even 3-dimensional space. We haven't really talked about 3 dimensions, but it's very similar to this. Good luck on the test.